Hey everyone, welcome to our section moving forward, kind of our last unit, I guess, for this current topic we've been on. We'll be dealing about balancing equations and different reaction types. And so here we're going to talk about reactions that are in aqueous solutions and specifically start to get into this idea of net ionic equations. So the way that we've been writing ionic compounds so far tend to look something like what you can see here. We've got silver nitrate mixed with sodium chloride, which tends to react to give silver chloride and sodium nitrate. And if you kind of notice here, there's a solid that's formed in the product side because of the double displacement reaction or double replacement reaction that's happening. So this equation doesn't show, like most ionic compounds, the fact that they actually get broken up or dissociated or separated into the cations and anions that they have when they dissolve in water. So in this case, we're just writing out the equation as we see it, but in reality what happens is these aqueous solutions actually kind of split apart into their cations and anions when they get dissolved in water. So for example, when sodium chloride dissolves into water, it separates into sodium, which has Na plus, and chloride ions, Cl minus, and similarly silver nitrate dissociates into silver ions and nitrate ions. So it's like they break apart when they dissolve in water, when they're aqueous solutions. A complete ionic equation really tends to show all of this happening. So it shows dissolved ionic compounds that are dissociated into their free ions that are kind of dissolved in water. So you can kind of see here everything is broken apart, and the only thing that's not broken apart is our silver chloride, because that is a solid. So it's not going to react with the water, dissolve in the water, because it's a precipitate, because it's a solid. After this, do you notice that there are some ions that are on both sides, the reactants and the product side? So when that happens, this is kind of like a math equation in that sense, in that they can actually be canceled out. So which ones are the same in the reactants and the product side? Well, we have nitrate, that's the same, so they can be effectively canceled out from our equation. They're showing up on both sides. Same thing with our sodiums, they're showing up on both sides. And so really, what's kind of left here, okay, with these being canceled out, is really just our silver ions and our chloride ions giving us our precipitate. So an ion that appears on both sides of the table and is not directly involved in the reaction, those are our spectator ions. So spectator ions are the ones that are getting canceled out. That would be a good term for you to kind of know moving forward with this stuff. Now, our net ionic equation, again, another term, is when the equation's written without including those spectator ions. It only shows what's important in the reaction. Okay? In writing balanced net ionic equations, the ionic charges have to also be balanced, and that's an important rule that's going to kind of come into play here. So ionic charges also have to be balanced as well. So consider the following equation. I've got lead plus silver nitrate gives us silver plus lead nitrate. It's a single replacement reaction. It's saying, what would this look like as a complete ionic equation? And then what would cancel out? So I'd like for you to pause the video and see if you can come up with what this would look like as the complete separated out equation. So if everything's broken apart, what does it look like? And then after that, see if you can figure out what the spectator ions are. So pause the video, give it a try, and come back when you're ready. Alright, so hopefully you got something along this line. Notice that the lead solid didn't do anything. And then we've got our silver and our nitrate broken apart into its ions, and our lead and its nitrate broken apart into its ions. And so what is canceling out here, and what can I keep? And so the NO3s, they're aqueous solutions. Okay, what would cancel out? Well, the only thing really in common here are these NO3s, right? So they're going to cancel each other out. And so really what would be left over here, well, I'd have Pb, it's a solid, plus silver, it's a solid. It's going to give me silver plus lead. Okay, that would be once it's balanced out. Now, again, afterward with this, we also need to kind of take a look and see about the charges as well. And we'll get to that point. But for now, it's just taking a look at the ions themselves. Okay, just canceling out. So, is the equation above balanced? Is it something that works out that it's an even charge on both sides? And the answer is no, right off. We have what is it? One lead and one silver and one silver. But if you notice here, we have a 2+ charge on the lead and only a 1+ charge on the silver. So how do we work this out to balance it? Well, we treat this the same way that we balance the other equations. We can only add numbers in the coefficients place. So if I wanted to balance out the charge on this, I would actually have to add in a 2 in the front of the silver, because there's a +1 charge. 2 plus 1s give me +2, +2 on the right. The charge is now balanced. But do the atoms balance individually? And the answer is no. I'd actually have to add a 2 in front of the silver to balance that out as well. And so what I see here is that I have this 2+ charge for silver, and canceling out the positive charges overall, so the charge is balanced, and the atoms balance as well. So a net ionic equation shows only those particles involved in the reaction, and it's balanced with respect to both mass and charge. So as an example, we've got an aqueous solution of iron 3 chloride and potassium hydroxide, and they're mixed together. A precipitate is formed in the product side, which is iron 3 hydroxide. It wants you to identify the spectator ions and then write out a balanced net ionic equation. So I'll get you to pause the video, give it a try, and come back when you're ready to go over the answer. Alright, so if we took a look at our balanced equation, or our equation, I guess, to start with, I'd have iron 3 chloride, so FeCl3, and it's an aqueous solution, plus KOH as an aqueous solution, and that's going to give me FeOH3, and it says it was a precipitate. There's my solid, plus KCl in an aqueous solution. So now I'm taking a look at this, and I'm going to try to break it apart into the ionic equation. So all the aqueous solutions are going to start to separate. So I know that iron has a 3+ charge when it breaks apart, so I've got my aqueous part there. Now, chlorine, do you see how there's 3 atoms of them there? So when it dissociates in its appropriate ratio, it's going to have its 3 atoms there. Because each chlorine has a -1 charge. And my potassium is going to separate, so I've got K+, and I've got my OH- as it separates. Our FeOH3, that doesn't change, it doesn't dissociate or dissolve in water because it's a precipitate, it's a solid. And then the potassium is going to change and dissociate into its ions, and same with the chlorine, dissociate into its ions. We identify kind of what those spectator ions are. So in this case, our spectator ions, something that's the same on the left and the right. So in this case, it looks like the chlorines would be the same, left and right. And the potassiums would also be the same, left and right. So here's my spectator ions. And really at the end of this then, I do have 3 chlorines there. To balance this out, I could put a 3 in the front here to show that, yes, they are the same. So our spectator ions have an equal charge. And really, I could write out the end result after that, or I could balance this as it is right here too, because I see I have 3 hydroxides in that precipitate. So I know that I'm going to actually have to have a 3OH right here to balance it out. So if I were to write this out now at the end with our spectator ions canceled out, okay, our potassium and our chlorine canceled out, then our net ionic equation would be Fe aqueous, which is 3 plus our OH aqueous. Actually, my mistake here. Iron is a solid when it separates out. Okay, iron is a solid element, and that gives us our FeOH3 as a solid. And I had a 3 here once I balanced it. Taking a look, does it balance out? I've got 1 iron and 1 iron left and right. I've got 3 hydroxides and 3 hydroxides left and right. If I look at the charges, do you see how there's no charge on the right hand side, which makes sense because we have a 3 plus charge on the left, canceling out with the 3 minus charge also for the hydroxide. So 3 plus and 3 minus gives a neutral charge. So this would be our net ionic equation, with our spectator ions being potassium and chlorine. So our last little bit is just taking a look at predicting the formation of a precipitate. So you can predict the formation of a precipitate by using the general rules for the solubility of ionic compounds. Will a precipitate form, for instance, when aqueous solutions of Na2CO3 and BaNO3 get mixed together? And so there's a table that we're going to reference that you're going to be given if you need it on anything. It's on page 344, and we can use that table to see if there's a solution that's going to be formed. So table 11.3, page 344, you can take a look at it. I also have it, just the general rules for them right here as well. And so what this table does is it takes a look and tells you what's soluble, so what is going to break apart into its ions, and what's insoluble, what's going to make a precipitate. It's not going to dissolve in water. So we have Na2CO3 and BaNO3 too. And we need to figure out, is this going to separate out? So, or am I going to get a precipitate? So Na2CO3 plus BaNO3. Well, if this thing, NO3. So if this thing were to go through a double displacement reaction, then it would really have to look like this: NaNO3 plus BaCO3. So really I'm looking here and checking to see, okay, does sodium nitrate and barium carbonate, will either one of those make a precipitate? So according to my list here, all nitrates, okay, all nitrates are soluble. So that means that this nitrate is going to be soluble. It's going to make a solution, AQ. Then I've got carbonate that I need to look at this table, and I need to see, will carbonate be soluble or insoluble? And it looks like that most CO3 compounds are going to be insoluble. So in this case, when I combine these together, I'm going to get a precipitate. I'm going to get a solid that's going to show up here. And so, will a precipitate form? Yeah, it will. Because of our solubility table, I can tell that barium carbonate is going to make a precipitate. It's going to make a solid. And so the table definitely isn't something you're going to have to memorize. It's just something that you'll have to understand how to use, because you'll be given it on any assessment or anything. So there are a couple of questions for you to try, just to kind of finish off this unit, and let me know if you have any questions.